Okay, let's go now to potential energy, gravitational potential energy. Imagine that we have a particle at the beginning at this position, right? And now gravity is acting. Later, of course, the particle is at this position, right? So we have initial position according to this reference level, right? Let's call this y initial, right? Initial position. Later the particle is gonna be right here, right? Y final. Okay, or final position. Perfect. Now let's see what should be the work done by gravity. Right? Remember how do we define work? Work is defined as the dot product of the force times the displacement. That's work. Okay, what is the force acting in this case? Well, the force is the force done by gravity, which is mg, right? The direction is negative, right? And in the j hat, right, direction, that, right, the displacement in the y direction, remember the magnitude is gonna be this difference, this is the magnitude, right? This is my delta y. The magnitude is this part, this distance, right, which is initial position minus final position, right? It's a vector. Displacement is gonna be negative. It goes down to gonna be negative, right? Negative. This difference, right? The difference, negative, right? The difference, okay, the product, okay, negative, the difference of initial position, right, minus final position, right, in that direction. Perfect. Now let's do it, right? So the product's gonna be mg, right, times initial position minus final position. Remember, we have the dot product, j hat, that j hat is equals to 1. Okay, great. Now this is equals to mg initial position minus mg, right, final position. Remember, every time we have a quantity multiplied by another quantity, we create a new quantity and we have to define it. Okay, let's define this quantity as the gravitational potential energy. So gravitational potential energy is defined as mgy. Got it? When we use this definition on the previous equation, what do we have? Well, we have that work then is equals to gravitational potential energy, right, at the beginning minus final gravitational potential energy, right? Now we can also rearrange this in this way, equals to negative, right, final potential, right, minus initial potential. This becomes, as you know, as negative, right, the change in the gravitational potential energy. So work done by gravity is equals to negative the change in the gravitational potential energy. Means what? This negative means that the potential energy decreases. If the potential energy decreases, how will it change? Negative. Okay, perfect. So what do we have then? The work done by gravity is equal to negative, right? The change of the gravitational potential energy. Okay, energy, gravitational potential energy has the same units, right, as energy work, right, which is joules. Okay, perfect. Now, let's compare this to the elastic potential energy we did the last time, right? Elastic potential energy, the same thing as gravitational potential energy, right? The work done by the spring is equals to negative, right, kx initial square, right, plus, right, k, right, x final square divided by 2, correct? We have that that condition. Actually, we have this is plus, right, plus, this is negative. We found this last time, right? And the same thing as before, right? We have, if we define if we define right here elastic potential energy equals to 1/2 kx squared, so we get the same condition, right? The work done for the spring, right, is equals to negative, right, the elastic potential energy of the spring. So you can see they have the same form, means that they must have something in common. Why do have something in common, right? It's gonna be the force, right? Remember, force work is equals to the dot product force times the displacement. So for these two cases, right, this force is a special force. We call this force a conservative force. Now let's try to explain this type of forces, conservative forces. Okay, we have right here, this is for gravity, right, the work, so that we're done by the spring, elasticity, right, equals to negative, right, the change in the elastic potential energy, where, right, gravitational potential energy equals to mgy, sometimes we call it this h, right, mgh. Okay, perfect. Now let's go to conservative forces. Right, these are the definitions of conservative forces. Conservative force in this case is related to work, right? Because work, look, as you can see, they have this, they were done by gravity, they were done by the spring, have the same form. Because they share the same type of force, right? Conservative forces. Okay, let's do it. By definition, right, a conservative force is coming with these points, right? A conservative force has these properties, right? Properties, right? Properties. Okay, we have these properties for the conservative force. One, it says that the conservative force is represented, the work done by conservative force is always coming right in this way. Is negative equals to negative change in the gravitational potential and potential energy. Could be gravitational or could be elastic potential energy. Okay, two, right, the work is reversible, right? Work, right, is reversible. Right, three, it says that depends only on the initial and final position, right? Work, right, done depends only, right, on the initial and final position and final, right, position, correct. And finally, number four, it says that the work done in a circular path, right, is gonna be a zero, right? For initial, if, right, initial position, right, is equal or the same as final position, right, is equal, right, to final position, works equals to zero. When you start right here, right, and go and enter the same position, right, the torque work is zero. Again, this is for the case when the force is acting is a conservative force. And of course, right, for all of these cases, friction is zero, right? No friction is taken into account. Okay, these are the properties again for a conservative force, like gravity, like for the spring, and like for the electric field. Okay, perfect. What should be a non-conservative force? Well, a non-conservative force gonna be friction, right? Non-conservative force, conservative, right, force, conservative force, right? Mainly we have friction. Okay, perfect. Now, we mentioned before, right, that the word done, right, the network, right, is equals to changing energy. Also, if we are dealing only with gravity, we can say that the work done by gravity, right, again, just taking gravity as the only force, right, is equals to the negative change of the gravitational potential energy, right? Now, when we combine these two, because also this one, when we're taking only gravity, right, in free fall, right, for free fall, for example, right, we take only gravity as the only force acting on the subject in free fall, right, for example, right? What is happening? Well, what is the net force acting on this object? Well, it's gonna be gravitational force, right? What should be the net work done by gravity? Well, the net work done by gravity is equals to what? Negative the change in the gravitational potential energy. But from the previous chapter, from the previous section, we found that in general the net work is equals to the gravitational change in the kinetic energy, right? When we combine these two right here, what do we have? We have that the network, which is also equals to kinetic energy, must be equals to change in the negative change in the gravitational potential energy or kinetic energy, right? Now let's rearrange this in this way, and what do we have? Right, change in kinetic plus change in potential is equals to 0. Okay, now when we are dealing with kinetic and potential, when we add these two energies, we call this the total mechanical energy, right? So the total mechanical energy is defined so far, right? Total mechanical energy, right? Symbol is defined as the kinetic plus potential energy. This could be kinetic, right? Potential could be this potential plus this potential, the total potential, right? And the total kinetic, right? This is the total mechanical energy of the system. Could be one object, two objects, and so on. Got it? Okay. Now, if we apply this definition right here, right? This is the definition for the total mechanical energy. If we have the change, if we make the change for the total mechanical energy, we have to make the change of these quantities right here, right? So this becomes change in kinetic plus change in potential, right? Got it? Look, and these two are very similar, right? Can you see it? The change in kinetic plus the change in potential must equal 0 means what? When there is no friction, in this case we have no friction yet, right? The change in the total mechanical energy must be 0. Can you see it? Okay, wait. When that happens, what do we have? We have that, one more time, change in the total mechanical energy is equal to 0 implies that the final minus initial equals to 0. Means what? This means that the final total mechanical energy is equals to total, right, initial mechanical energy. Correct? This means that energy is conserved. So we have the conservation of energy. It's the same at the beginning and at the end. Doesn't depend on time. Right? So again, this is a very important conclusion, right? And we call this the conservation of mechanical energy, right? Conservation of energy or mechanical energy, right? Okay, we represent it in that way, or we can represent it also in this way, right? What should be the total mechanical energy at the end or at the beginning, right? We can start at the beginning with 1, 2, it's going to be the same thing, right? Kinetic initial plus potential initial equals to what? Kinetic final plus potential final, right? This is kinetic for the whole system, potential of the whole system, right? could be elastic plus gravitational, right? The same thing in the other side, right? This is the same thing as this one, conservation of energy. And this is happening only when we have no friction. Okay, we have this representation. Now, what happens if we involve friction? How it works? Okay, let's do it. Let's do it. Imagine that we have this case. Again, the initial is equals to final, right? This is very important. Conclusion. And one more time, why we always try to get or to finish the concept for each subject with kinetic with energy, because energy must be conserved, right? That's why energy is important, because must be conserved. Okay, great. Now, let's see what happens when we involve friction. Let's do it. Imagine that we have this incline, right? Like this. Okay, this incline like this. We have an object at the beginning right here, right? And later the object is right here. And we apply a force, right? This is an external, we apply force or other forces. Sometimes we call other forces, right? Or applied force. So the beginning was right here and it was right there, right? We have a displacement in this direction. Also, we have a change in y, right? Change in y. Okay, let's do it. Let's see. Let's find the total work. But instead of work, let's start with forces by using Newton's second law. Let's use Newton's second law. Okay, what do we have? Forces acting, okay, on this object is gonna be what? Gravity, right? mg. Remember, in this case, we have displacement in this direction, it's x, and it's gonna be our y according to the reference frame, right? Now let's do it. What should be the net force? Remember, using Newton's second law, net force, right? Net force is the sum of all the forces, right? Forces acting, well, we have this one, right? Friction, gravity, and the applied force, right? So what do we have? The work done by, or the force done by gravity, right? As a vector plus what? Plus the applied force, right? Plus what? Plus the force done by gravity must be equals to what? Mass times the acceleration, right? But the frictional force, right, equals to mass times acceleration. Okay, now let's do it. What should be then in this direction? Well, the direction, the motion is in this direction, the acceleration, right? Now let's take this as our positive, right? So what do we have in the, let's say, positive direction? We have this one, right? The applied force. Okay, we have the applied force. Okay, let's use components, right? Applied force is, let's say, in the x direction. Applied force, right, is positive. Minus what? Minus friction, right? Minus what? Minus this component, right? You know this from the previous chapters, right? This is mg. What should be this component? mg sine theta, right? It's a negative respect to this direction of motion, right? So it's going to be negative mg sine theta, right? Equals to what? Equals to mass times acceleration, positive in that way. Got it? Okay, now let's multiply by d, right? All of this by this delta s, d or this delta s. Okay, let's do it. Let's do it. We multiply by this delta s magnitude, right? So what do we have? Applied force times s minus fk times s, right? Minus mg sine theta times s. Okay, where? Okay, s right there. Okay, mod equals to what? MAS, right? The distance, right? This magnitude of the displacement, right? But what is force times 4 times distance? Remember, 4 times distance is equals to work, right? When the displacement and the force are parallel, right? When the force and this and the displacements are parallel, well, the work is just the product of the magnitudes, right? Perfect. So what do we have then? It's gonna be work done by the applied force minus, what is this? What is that? It's gonna be the work done by friction, remember? It's gonna be work done by friction, right? Work done by friction, right? Minus, what should be this magnitude? Well, look, let's pay attention again on this path, on this triangle, right? When we are going to this triangle, right? We found that the object change, right, increases the potential energy, right? So we have this angle right here. How are these three quantities related? Delta y, right? Delta s and theta, right? How are they related? They're related by sine, right? Look, sine theta is equals to delta y over delta s, or just s, the magnitude, right? I use the s and s right here, but also we can use delta s, the same meaning. Got it? So right here, what do we have? Delta s, or s, right, times sine theta is equals to what? Delta y. Correct? So means that this product right here is just delta y. And what is that? This term. So this term becomes mg, right, delta y. And what is the mg delta y? Is going to be the work done by gravity, right? Gravity is equals to change in the gravitational potential energy. Perfect. Then there becomes this analysis goes to, at the end, right, we are right here, right, the work done by the applied force, right, minus, right, the work done by friction, right, I'm right here is gonna be minus the work done by gravity, correct? Perfect. So far so good. Equals to what? Equals to mass times acceleration times the displacement. But remember, before we found that mass times acceleration times the displacement is equals to the change in the kinetic energy, right? Okay, so means that is equals to the change in the kinetic energy. Correct? Perfect. Now let's go in this way, right? Let's go in this way. I'm looking at this sign right here. Remember the whole, how do we define the work done by friction? One more time, right? Work done by friction is equals to negative, right, FKS, right? So because right here we have negative, right, negative, so the whole thing is gonna be, right, the work done by friction. Okay, perfect. So this is the work done by friction. And then what do we have? Well, we have that if we send this term to the other side, what do we have? We have that the work done by the applied force plus the work done by friction, right, is equals to change in kinetic energy plus change in potential energy, right, gravitational potential energy. But what is this? This is just let me see. Well, remember we found already this one, right? It's not right here, but let me put right here. We found before that the change in the total mechanical energy equals to the change in kinetic, or the change, right, in potential. Remember that one from the previous analysis? Okay, great. So means again that this is equals to, right, change in the total mechanical energy, right? Change in the total mechanical energy, right? Usually we take this equals to 0, right? If the work done by the applied force equals to 0, then what do we have? We have that the change in the total mechanical energy is equals to the work done by friction. So it means that when we have friction, right, the change in the total mechanical energy, which is what? Change in kinetic plus change in potential, is equals to the work done by friction, right? If we have no friction, again, we get to the conclusion that the change in the mechanical energy, torque mechanical energy is equals to 0. This is with no friction, right? It's conserved. When we have friction, that change is equals to the work done by friction, by kinetic friction, right? Got it? Okay, and that's the conclusion for this analysis. When we have friction, right, the change in the torque mechanical energy is equals to the work done by friction. Got it? Perfect. And finally, in this section, in this chapter, because we finished already the chapter, right, regarding to working energy, we go to power, right? In this case, we are dealing with conditions where energy is not changing, it's constant, right? But what happens when the energy changes in time? When the energy changes in time, or work, right, in time, what do we have? We have power. Power. And power is defined as the change in energy or work, right? Work, right, respect to time. Correct? Okay, or we can define also, or we can say work, right? But how do we define work? Work is the change, right? Change kinetic, change potential. We can say, right, change in the torque mechanical energy, right? Okay, we can use it like that. We can use just kinetic or potential. The idea is the same, right? Imagine we're dealing with kinetic, right, respect to time. So we can use either one, work or energy, because they're related. Okay, perfect. And then again, this is the definition for power, and the unit of power unit is watt. Watts, right? Watts. That's the unit of power. Also, because work is equals to, right? The symbol for power is P. Work is equals to force, right? That parallel force, right? Delta S, right? If we now divide it by delta T, right? What is this ratio? This is just velocity, right? It's gonna be then force that velocity. So another way how we can represent power, right? Power is a scalar. Usually when we're dealing with power, we're dealing with the average power, right? Average. Also, we can have the instantaneous using the same definition as, right, in calculus, finding the limit, right? But in general, we use again the average when we're dealing with power. Okay, and with this, we finish this chapter and see you in the next chapter. Bye.